Now I'm together with Lukas Ostendorf, who has developed, hello Lukas, who has developed a very interesting method to make the HAMNET available to people who don't have line of sight. So Lukas Ostendorf, the audience, I'm proud that I can present Lukas Ostendorf and talk to you. He's a computer engineering student at RWTH, Rheinisch-Westfälische Technische Hochschule Aachen, here in Germany, at Aachen University. And during his master thesis, which is done at Roth and Schwarz, he has designed a project called HNAP, a communications protocol for HAMNET access in the 70 centimeter band, which allows access also without line of sight. And that's for the Pluto SDR, and it's about implementing the HAMNET access protocol on the Adalm Pluto SDR. And the HAMNET access protocol provides a spectrally efficient access with low latencies to the HAMNET using a 200 kilohertz duplex channel in the 70 centimeter band. And the complete HNAP stack has been implemented on the Adalm Pluto SDR, allowing standalone operation without any additional processing PC. The implementation was done in plain C during the liquid-dsp library, using the liquid-dsp library and the Pluto's ARM CPU. And this talk will introduce the HNAP protocol and then show how the implementation of on the Adalm Pluto was achieved. So I'm very looking forward to this talk, because I've also implemented quite a lot of HAMNET projects and create a lot of HAMNET links and also access points in the past years. So this will be an interesting enhancement to this really good project. Okay, my studio team will now play the pre-recorded video. Dear audience, please feel free to comment and discuss already during the video in the YouTube chat. Sebastian, please go ahead.
Hello everybody, my name is Lukas Ostendorf. I'm a student of the RWTH Aachen University, and I did my master thesis at Roth and Schwarz, where I developed a new protocol for easier HAMNET access, the HAMNET access protocol. So, as the name states, HNAP is a new protocol who tries to extend the existing HAMNET, especially extend the existing HAMNET coverage. So HAMNET itself, it's the high-speed amateur radio multimedia network, an IP network separated from the internet by only using directional radio links in the 2.4 and 5.7 gigahertz frequencies. There's one big problem with the HAMNET network, because we use those high carrier frequencies, 5.7 gigahertz or 2.4 gigahertz, the access, in order to get access to the system, every client has to have a line of sight connection to an existing HAMNET station. And as you can see here is a map on the right side from HAMNET base stations around Munich, and the link distances could be quite large, so more than 100 kilometers. So sometimes it's really hard to get a line of sight access to the system. So this limits HAMNET's coverage currently. Now, HAMNET exactly tries to fix this problem. HNAP, as I told before, is a result of my master thesis as Roth and Schwarz. And in the thesis, we try to enable the use of a 200 kilohertz duplex channel in the 70 centimeter band. Using the 70 centimeter band has a huge benefit because of the low carrier frequencies. Also, non-line of sight access could be provided. So the idea is, as you can see on the right side, we develop a new protocol and a new base station, which will provide access via the 70 centimeter band. And this is just the first hop to get into the existing HAMNET backbone. So when we started the thesis, we first set some system requirements. We want the whole system to be voice over IP capable. This means that we have to achieve an application layer to application layer one-way delay of less than around 150 milliseconds. We want the data rates to be adaptive. So a user who uses a very good directional antenna, or probably is close to the base station, should benefit from this and achieve really high data rates. But at the same time, we also want to have a good coverage overall. So we have to support some robust but slow modulation schemes too. The whole system design should be flexible regarding the bandwidth and also flexible regarding carrier frequencies. So because in Germany we have, for example, this 200 kilohertz channel available that we are going to use, but probably in Great Britain wider bandwidths are available, or we have to deploy it on smaller bandwidths, probably also on different carrier frequencies, for example, in the 23 centimeter band. So our system should be reconfigurable to also use wider bandwidth without too much effort. Finally, the hardware should be somewhat cheap. So we set a price tag for the client hardware less than 300 euros, and the base station can be somewhat more expensive, up to 1,000 euros. The idea behind this is that for a base station, with this price tag, we can afford to have a duplexer, so the base station will run in full duplex mode. And for the client, we just spare the cost of the duplexer, but therefore we have to restrict the client to half duplex operation. Here's the system that we came up with. So it's an OFDM-based system with 4 kilohertz sub-carrier spacing. We chose OFDM because with OFDM it's really easy to reconfigure the system bandwidth. We just define either more or less subcarriers to be modulated, and this changes the system bandwidth really easy. So for our application scenario of a 200 kilohertz channel, we defined that 40 of those channels, of those subcarriers, will be modulated, resulting in a 160 kilohertz system bandwidth. Another benefit from using OFDM is that we have a cyclic prefix, which you can use to combat any inter-symbol interference. So also if we have large links, probably non-line of sight with a hard multipath, the cyclic prefix should be long enough to combat any of those inter-symbol interference. Our structure is an FDD TDMA-based system. So when choosing the system structure, we first had a look at OFDMA-based or CDMA-based system, which would have a benefit that multiple clients can transmit simultaneously, probably lowering the delay. There's a big problem when we use OFDMA or CDMA, because if we have only one client with a nonlinear amplifier or some other bad hardware conditions, this client will also affect the signal of all other clients which are currently transmitting at the same time. So the overall system performance will degrade severely. When we use TDMA instead, only one client transmits at a time. So if, again, this bad client with a nonlinear amplifier appears itself, so the client will have a bad connection, but it won't affect any other users. And since we cannot guarantee that everybody uses certain amplifiers, in the end it's the amateur radio community, so probably many will use their own amplifier, which shows this TDMA system because it will be more robust. The modulation, as we wanted an adaptive data rate, we decided to go with qualitative amplitude modulation and defined modulation schemes from QPSK up to QAM 256. And we combined this with a convolutional coding of rate 1/2 or 3/4. Now, here's the TDMA frame structure. We defined one subframe to have a length of 17 milliseconds, and one subframe will contain 4 uplink slots and 4 downlink data slots that each client can use. As you can see here in a slightly darker blue, every subframe starts with a downlink control slot in which the base station broadcasts the slot assignments, and every client, after decoding the slot, will know when he has to receive or when he is able to transmit. Furthermore, we have one uplink control slot here, These slots are required because we have a request grant system in the uplink. So every client first has to request some transmission using this control slot, and then the base station will assign the larger data slots to the clients so that they can transmit their data. Now, finally, at the MAC layer, we designed the system to be transparent to the Ethernet layer. So our MAC layer will simply accept Ethernet frames and forward them. And in the end, our MAC layer will also output Ethernet frames again. This has in my opinion, huge benefit that the overall system can just be viewed as one big Ethernet switch. So a client just sees it as an Ethernet switch. And we have another benefit that we do not have to care about the interface to the higher layers, because for interfacing with the network layer IP stack, we already have the address resolution protocol defined, and these implementations are already there in Linux systems, so we do not have to care about it. Since Ethernet frames can grow up to 1,500 bytes in size, our system has to support fragmentations. Fragmentation, as you've seen before, the subframe structure is quite short. So one downlink slot contains up 60 up to 250 bytes. The Ethernet frame is way larger, so we have to fragment the Ethernet frame in some cases. Scheduling at the MAC layer is done in a round-robin basis. So the scheduler at the base station just iterates over all clients who have pending requests and assigns them in a round-robin scheme. The scheduling period is really short, so every subframe we have a scheduler being run. We chose it to have such a short period because this really lowers our delay, and we want to have the system to be VoIP capable. So a short scheduling period will help us keeping the delay low. And next, we will have a look at the implementation. For the implementation, we chose the Adalm Pluto SDR. The transceiver of the Adalm Pluto SDR supports one RX and one TX channel. They can transmit in full duplex mode. The tuning range is 325 MHz to 3.8 GHz. The main processing unit on this Pluto SDR is a Xilinx Sync. This system on chip comes with an ARM Cortex dual core on which a Linux system is being executed. And on top of the Linux system, we wrote our application, which implements the HAMNET protocol. And in addition, there's a small FPGA, which will be responsible for decimation and interpolation of the baseline samples. Cost of the system is only 150 euros, so it very well fits our selected price range. A client can even afford to buy another power amplifier. Now, here's the functional overview of our C application. We've written the whole application for Linux in C by using the liquid-dsp library. If you've never heard of liquid-dsp before, you should definitely have a look at it. So it's an open source library which implements many digital signal processing functions. For example, there's a PLL, there's a least mean squares equalizer, and a basic OFDM framing scheme. It really helped a lot during implementation of the application. Then the basis of our application is an abstract platform interface. So we have some well-defined interface function to our file layer, which makes the whole platform interchangeable. So it would be possible to switch from a Pluto SDR to another SDR. But also, very important, it allows us to have a simple integration of the simulation environment. So we wrote a basic simulation which includes Rayleigh fading, multipath, and Gaussian noise to test how well our PHY and MAC layer work. Finally, after the MAC layer, we have a Linux tap device. So Linux tap devices are virtual Ethernet interfaces, which can be created in a Linux system. And an application can connect to a tap device and then just read Ethernet frames from the tap device, and also write Ethernet frames to the tap device, which are then forwarded to the Linux network stack. So this is the way we achieve the Ethernet transparency I've mentioned before. Now here's an overview of the threading structure of our system. You can see at the bottom we have our RX path, and at the top we have our TX path. So overall, our application consists of 5 threads. The first threads here, the file layer threads, are interfacing with via liquid-dsp with our transceiver buffer. They run on one isolated core because we have very tight latency restrictions here. Apart from buffer transfer, they are also responsible for the FFT, for the OFDM system, and some channel equalization. And then on the RX path next, this is responsible for receiving the slots. So it does the demodulation of the QAM signal, VTEL decoding, and then forwards it to the MAC layer. And finally, at the MAC layer, we also push to the TAP device if we have received a complete Ethernet frame. In the TX path, we have first a TAP RX thread running, which continuously monitors our TAP device. And whenever this thread receives a Ethernet frame, it will then queue it to the MAC queue. Then at the MAC thread, we have our scheduler, which is executed every 17 milliseconds. And the scheduler, or the MAC thread, is then also responsible for fragmentation and already responsible for forward error correction and modulation of the slots. And then these pre-modulated subcarriers are forwarded to the file TX thread and then transferred to the buffer. Our system, so these RX and TX paths, are synchronized via the buffer read and push operations. So the liquid-dsp buffer receive and buffer push are blocking operations. So once they are set up, the buffer are implicitly the threads are implicitly synchronized. Now, at last, regarding the implementation, I want to focus on how we achieved real-time execution, because if you just would compile the C application you've seen now and put it on a stock Pluto, the system just won't run in real time. There would be lots of timing issues. This is caused because the default Linux system on the Pluto, or any default Linux system, has a sometimes high latency when scheduling threads caused by interrupts and other kernel operations. So we use the Linux real-time patch and Linux real-time priorities in order to lower the latency of the scheduling. In addition, you've seen we use pthreads to distribute the load across our 2 CPU cores. And finally, we even have to isolate the one core where the buffer transfer takes place, because this isolating the core effectively removes any interrupts from the specific CPU core. It also prevents all user applications from being executed on this core. So really all of the processing power the core offers is dedicated to our 2 PHY TX and RX threads. At last, we also had to optimize the VTEL decoder. So when we were looking for a VTEL decoder, there are lots of implementations available, also optimized, but mostly optimized for Intel CPUs. Now, we are having an ARM CPU here, and ARM also has its pendant to the fast Intel SSE instructions, which are called ARM Neon. But we could not find an open source implementation for a half-rate VTEL decoder. So we just ported the SSE libfac decoder to ARM Neon instructions, which gave us 3 times the speed up and allow us to get high data rates and decode these data rates in real time. Now, finally, we will have a short look at our system. So here you can see a terminal view from SSH login to one Adalm Pluto. You can see the Ethernet interfaces here. So at the bottom, we have our USB interface. USB 0 is Ethernet via USB, so it's the connection to the host PC. And you can see the tap device here. This is the virtual Ethernet interface, which is connected to our HNAP protocol implementation. And as it's now a Linux system, you could configure it as you'd like. For example, if you want to forward HAMNET access to your host PC, just create a network bridge from tap 0 to USB 0, and your host PC will be in the network. Or you can employ real routing and probably do a subnet, forward a subnet to this USB interface. So really, you can configure it however you like. It's really flexible in this way. Finally, some more hard facts about the system. On the left side, you can see the ping command being executed via HNAP. We reach an average delay of about 140 milliseconds round trip time. So this is not a one-way delay, it's the round trip time. I would like to note that when we only consider the downlink, our downlink has really an excellent delay of 10 to 20 milliseconds. But the uplink is initially way slower because we have this request grant system in the uplink. So initially a packet has a delay of 110 to 120 milliseconds. If we would start a streaming application now, the delay in the uplink will be decreased slightly. Finally, you can see some data rate measurements on the right side for our different modulation coding schemes. So you can see with UDP, we reach up to 380 kilobit per second, and with TCP, we can reach up to about 300 kilobit per second. The TCP data rate is slightly lower, just because in TCP, we have to transmit the acknowledgements. And since we are only half duplex, whenever we transmit acknowledgements, we cannot receive anything, so our downlink data rate decreases. You can also see we could not get any stable measurements for MCS5 yet. That's a problem because this is the fastest modulation coding scheme, and the CPU load is close to 100% in this case. So there are sometimes some timing errors so that slots are not received in time. Now, finally, at the end, what's left to do? What do we still have to do? Sadly, we could not perform any tests in the real world with a power amplifier. This could be an issue, or this could be difficult because we use OFDM in the end, and OFDM comes with a very high peak-to-average power ratio. This means we have to use linear amplifiers, and we also have to operate them far from the peak output power. So it will be hard to really get up to the legal limit in terms of power. And we still have to see how far the link distance will be that we can achieve. And additionally, most of the tests I've performed so far were either done in simulation or without any power amplifier, so with a distance of, let's say, 10 meters or 20 meters. So we have to perform real-world tests in bad channel conditions. So with a high multipath, with a high delay spread, and a bad S2N. Finally, something regarding the implementation. Currently, the only mode that I've implemented so far is an unacknowledged mode at the MAC layer. So no acknowledgements are being transmitted. This is good if we want to use streaming applications like voice over IP, because a certain frame loss is negligible in this case. But if we want to have data transmission, it would be probably better to implement an RQ scheme. Yeah, so that's it. I hope you get some interest into this project and want to try it out yourself. So just visit hnet.de our GitHub repository, HNAP for Pluto SDR. There you can find more information. You can also find a firmware that you can download and flash onto your Plutos. And if you're interested into more details of the overall protocol and into details on the system design, also the thesis will soon be published at hnet.de. So thanks for the attention. If you have any questions, I hope we have some time left for these, so feel free to ask.